Alright, for this problem we're going to prove that summation k equals 0 to n of n choose k is equal to 2 to the n, and we will interpret this in terms of Pascal's triangle. And for this one, it's actually a bonus. I'm going to give two different explanations for why this works. The first explanation, so proof number 1, will rely on the binomial theorem that x plus y to the n is equal to summation k equals 0 to n of n choose k x to the k times y to the n minus k. So that is the binomial theorem that allows us to expand out x plus y to any integer power. Now this is always true, and I'm going to plug in certain numbers for x and y to end up with this. So I will just simply let x equal 1, and I'll let y equal 1. In that case, I would have 1 plus 1 to the n is equal to summation k equals 0 to n choose k times 1 to the k times 1 to the n minus k. So everywhere I see a x, I replace by 1. Everywhere I see a y, I replace by 1. The left-hand side becomes 2 to the n. The right-hand side becomes k equals 0 to n choose k times 1 times 1. So I just simply get 2 to the n is equal to summation k equals 0 to n choose k. So that's the proof. Now let's interpret this in terms of Pascal's triangle. So Pascal's triangle starts off with 1s on the sides, always, and then to get the middle numbers, we would add up the two entries that are above. So this number would be 1 plus 1 is 2, 1 plus 2 makes 3, 2 plus 1 makes 3, and then if I just keep adding like this, 3 plus 1 makes 4, I would get the terms in Pascal's triangle. Now what this equality means is that if I add up the numbers going horizontally, so if I get the powers of 2. So for example, 1 is, if 1 is 1 by itself, 1 plus 1 is 2. 1 plus 2 plus 1, that's 3 plus 1 makes 4. 1 plus 3 is 4, plus 3 makes 7, plus 1 makes 8. I'll do one more. 1 plus 4 is 5, plus 6 makes 11. Plus 4 makes 15, plus 1 makes 16. And you can guess what this one's going to be. That's going to be 32. If I just add across, I get 32. And so that's what this equality means in terms of Pascal's triangle. So that's the answer for 425. Now this one actually has a bonus argument that this actually has a combinatorial argument for why this inequality works. So proof number 2. And I'll do this with 4. So I'm going to illustrate this with n equals 4. The general case is actually in the textbook. I'm going to illustrate this with n equals 4. So 4 choose n, or 4 choose k, is the number of ways of choosing k objects from a set of 4 objects. So for example, if I have 4 objects, 1, 2, 3, 4, 4 choose 1 would be the number of ways that I could pull out an argument. Okay, so 4 choose 1. So how many ways can I pull out 0? Well, there's only one way to do that. So imagine that I'm flipping a coin, heads, 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 heads. I flip a coin 4 times. Now let me list out the possibilities for flipping a coin 4 times. Heads, 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 heads. Heads, 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 tails. Heads, heads, tails, heads. Heads, heads, tails, tails. And I'm just going to list out the possibilities for the different ways that I can flip a coin 4 times. Now, if as I'm writing this down, if you know some computer science, or if you've taken a class in with base arithmetic, you recognize that I'm basically writing in binary with h's replacing zeros and t's replacing ones. And so those are all the possible ways that a coin can be flipped 4 times. Okay, now I'll interpret this to be when I pick a number from this box, that means that I get a head on that number. So how many ways are there of getting one head? Well, there are, I'm going to circle these, of getting one head. Here's this way here, there's one. There's another way here, that's 2. There's another way here, that's 3. And another way here, that's 4. Here, the head came on the first one. Here, the head came on the second. Here, the head came on the third. Here, the head came on the fourth. And that corresponds to the possible ways of drawing one number from this list of 4 numbers. So there's 4 choose one ways of selecting that, and just like there's 4 choose one things that are being highlighted, or that are being circled in red right now. Now, how many ways are there of picking 2 objects? Well, there's 4 choose 2 ways of doing that. The possibilities are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Now, all of these correspond to what configurations over here. So if this means head on the first, head on the second, that would be this one here. Head on the first, head on the second. 1, 3 would correspond to this one. Head on the first, head on the third. 1, 4 corresponds to this one. Head on the first, head on the fourth. 2, 3 corresponds to this. The head is on the second and the third. 2, 4 corresponds to this. Head on the second, head on the fourth. And finally, 3, 4 would correspond to this one, where the heads are on the third and the fourth. Okay, next let's talk about what happens if I have 3 objects being pulled. So there's 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. There are 4 choose 3 ways of pulling 3 objects from these 4. Now that corresponds to the different arguments here. So I'm going to write this in kind of bubbly like this. This one right here corresponds to 1, 2, 3. Head on the first, head on the second, head on the third. This one here corresponds to 1, 2, 4. Head on the first, second, and fourth. This possible scenario corresponds to head on the first, third, and fourth. First, third, and fourth. And this one here corresponds to head on the second, third, and fourth. And then there's one way of getting all heads, that's 4 choose 4. And then there's one way of getting all tails, 4 choose 0. So if the empty set for all of them are 1, 2, 3, 4. So 4 choose 4 ways of doing this, 4 choose 0 ways of doing this. So if I add all of these up, I have to get the total number of ways of flipping 4 coins. But the number way of flipping 4 coins is clearly 2 to the 4th. There's 2 possible ways of flipping a coin on the first flip, 2 ways of doing the second, 2 ways of doing the third, 2 ways of doing the fourth. And so if I add these 5 numbers in Pascal's triangle up, I must get 2 to the 4th. These are just 2 different ways of counting the number of ways that 4 coins can get flipped. Now this is a special case using n equals 4. The general case is exactly like this, that I can do the exact same argument to show that no matter what the value of n is, 2 to the n is equal to summation k equals 0 to n choose k. And that corresponds to different ways of flipping n different coins. So I personally think that this argument is the quickest and most elegant. However, there is a second interpretation that where I actually consider these as ways of flipping a coin, and then this would be the total number of ways that the coin gets flipped.